Good morning, everyone.
Good morning,
Morning,
doctor.
doctor.
Morning, Doctor.
So I have provide additional notes inside the e-learning. Okay, so have you downloaded the new notes?
Yes.
Yes.
This is the additional notes. So this is voltage divider bias, where we apply the Thevenin theorem. And then this is another exercise. We have this circuit, alright, you know how to. Firstly, what we can do is simplify the first is to simplify the circuit, and then we apply the Thevenin theorem, right? And then we can find the VTH and RTH, right? Over here. Okay, at the bottom of the circuit, we can apply the Thevenin theorem. And then here we can do after we simplify the circuit using Thevenin theorem, we can apply the Kirchhoff voltage law over here, and then we can get the current, right? Okay, so we can get the current, and then we can find the IC. Okay, for DC analysis, you can find several parameters such as the currents and also the voltages. However, when you do the AC analysis, the important value to find is only the IC. Okay, IC, the current over collector. Alright. Okay, so this is another example. We have emitter bias. Okay, so here you can go through after this. Right, so here is the example of the circuit. So here you can apply the KVL over here. Okay, so from VCC to VEE. And then so here is the solution over here. Okay, you can try if you have, this is the solutions, and then you just apply the value inside the equations, and then you can get the IC, VC, VE, VCE. Okay, so there is one friend asked, is the IC is ICQ? Okay, so when you find the IC, when you find IC, is the IC is ICQ. So is IC equals to ICQ. So how you want to know this? Okay, so when you apply all the theories, when you apply all the KC of current law, KCL, KVL, the Thevenin theorem, you can find the IC, IB, and this all the parameters here. And then how you know either the current that you determine is ICQ or not. Okay, so usually for the example, we must provide to you the ICQ actually. Okay, because if we want functioning circuit, so we in order to get a functioning circuit, we must determine the current that can give a function to the circuit. Okay, and also for your case, we know that you have the load line. Okay, you have the load. Oh, I think there is a slide over here. Okay, so there is a load line over here. Okay, IC and VCE. Here the IC will be varies, right? So there is so either our IC that we found is ICQ or not. Okay, so ICQ, actually the value that we find must be at the middle of the graph. Okay, so as long as it is not provide the IC with VCE 0, that means our IC that we find is ICQ. Okay, so for this case, we see that the IC is 1 milli and your VCE is 9.7. So here your VCE is not 0. Okay, if your VCE is 0, you know that it is in the saturation region. Okay, so when you find the IC, you can determine the VCE. Okay, so from that two value, you can relate either the IC and VCE is Q point or not. Okay, so as long as it is at the middle of the graph is okay. Okay, so that means the IC and VCE is the Q point. Okay, so we can use the IC equals to ICQ. Okay, all right. So here, this is another example. Okay, so for this one, you just apply the KVL across this node from VCC to VEE. Okay, then you can find the answer. This one you can try later. Okay, I want to focus on. Okay, so this is another example when you are given data sheet. Okay, so how to read this data sheet? Okay, so for example here, this is the circuit on top of this. Okay, the circuit here said that the BJT is NPN transistor 2N3904. Okay, so it just give you the model. Okay, the model for the BJT. So what you can do is read from the data sheet. Okay, 2N3904. Okay, so here in the data sheet, they will provide you the total power dissipation. This is at room temperature, right? So here your PD is 265. And then here it gives you a VCEO. Okay, VCEO means the collector emitter voltage. So the maximum value it can be is, this is the maximum rating. So maximum of the VCEQ, okay, must be equals to 40 volt. So what you can do here, okay, so from the power, you get the power 265 milliwatt and the VCEO is 40 volt. Okay, so IC also given in the datasheet is 200 milliamp. Okay, so the maximum must be 200 milliamp and your VCE maximum is 40 volt and the power is 265 milliwatt. So actually, so here it give you the question asks you how much is the maximum VCC. Okay, that's why what you read from the datasheet is the maximum power, maximum VCE, and also maximum IC. Okay, so from this value, you can determine what is the maximum VCC can be applied to the circuit. Okay, can be applied to your circuit, so it can, your circuit still can be functioning. Okay, so actually here your VCC equals to VCE plus VC over here. Okay, the KVL here. Usually your circuit is, so here usually your circuit is something like this, VCC, here is RC, here is VCE. So you apply the KVL over here, you get VCC equals to VRC plus VCE. So this is the equation. Okay, VRC equals to ICRC. Then you can just put all the value that you read from the datasheet. Then you can find that actually the VCC equals to 59.5. So this is the answer. Okay. And then this is from the previous class. The question gives you Q point over here, but asks you to find the VCC, RC, and RB. So instead of find the Q point, now the question asks you to find the VCC, RC, and also RB. So from the graph, you must read the value for Q point. Actually, can you hear my voice or my mic is too slow?
Yes.
So from the Q point here, you read what is the VCE and also IC. So because this is a Q point, you can write it as ICQ. Okay, so you have the circuit. You know how to determine the KVL. Okay, so here is KVL1. Okay, so we have IC and VCE. So IC is at the collector terminal, right? So ICQ over here, VCEQ over here. So you just put these two value into the KVL number 2. Okay, so you get the VCC and RC. And then from the same KVL, okay, from the same KVL, we can find the value for the saturation value and also the cutoff value. Okay, so here also another trick. Okay, so 40 is when your IC equals to 0, your VCE is 40. So you put the value inside the KVL, okay, IC equals to 0, VCE equals to 40. Okay, from this. Okay, so from this point, you get one value over here. So here you know that your, because IC is 0 at this time, okay, so here you know that your VCC is equals to 40, right?
Yes.
Okay, so you get the value for VCC, and then you just put the VCC value inside KVL number 2 here. Okay, so what you get here is 40 equals to IC is here. How much is this? ICQ? 3, 4, 5, okay, around 5.5 maybe. 5.5 millivolt. Okay, RC is what you need to find. Plus VCE. VCEQ is 24 maybe. Okay, so you just read here, I just write 5.5 milliamp. VCEQ equals to 24 volt. Okay, so you can, so now you get the value of RC. And then you need to find the RB. Okay, so RB you need to have VCC, and also here is IB. So over here, how much is your IB? Okay, because the question didn't give you beta value, okay. Beta not given, but it give you Q point. So here you need to read IB. How much is the IB value over here? Okay, so ni lebih kurang.
18,
Masih
94
around
ampere.
maybe 18 or 19 maybe lah. So it depends on how you read the graph. So here maybe, I'm not sure how much is this, because if you draw the line properly, you get a estimation value is, so IB here is 18 micro, right? So you put it on the KVL1. KVL1 is VCC equals to IBRB plus VBE. So VBE, you can use the 0.7 value. So now you get the IB value. Okay, so this is example reverse calculation, okay, because you have the Q point, and then you need to find the resistor and the voltage value from the circuit. Okay, okay, sempat silent. A new subtopic now. Alright, so now we continue with a new subtopic. Alright, so before this, if you see on our previous examples, okay, so here, most of our example previously, if you look at the circuit, okay, so if this is a collector base emitter, at emitter terminal of your BJT, there must be a capacitor. Okay, so this is what happened during AC analysis. The capacitor is fully charged. Okay, when the capacitor is fully charged, it is short circuit. That's why during AC analysis, your circuit is grounded over from emitter terminal to the ground, because the capacitor, okay, because the capacitor here is fully charged. Okay, so when it's fully charged, it can conduct current, right? Okay, it can provide voltage as well. So that when you do the AC analysis, you short circuit your RE. Okay, your RE over here, your RE is shorted. Okay, because your capacitor is allow the current to flow through it. Okay, so here what happened is you can get a simplified from the emitter terminal to the ground. Okay, so now we want to learn when there is no bypass capacitor across the RE. When there is no bypass capacitor across RE. Okay, so this is a simple circuit where you can see there is no bypass capacitor over it. Okay, no capacitor over here. So what happened during AC analysis? Okay, AC analysis. So you must draw the RE. Okay, you must draw the RE. Okay, so when there is no bypass capacitor at RE, okay, when you draw, can you hear my voice?
Yes, yes.
Okay, so when you draw the AC analysis, what happened at the emitter terminal is you must draw the RE. You must draw the RE. So when you do the AC analysis, so here is firstly at middle frequency first. Okay, at middle frequency. So from C to E, okay, so you have three terminal CVE. Okay, so from C to E, you must draw the current independent source over here. Okay, GM by pi. So the arrow is here. Your C is emitter. Okay, so from the current to emitter, you have a current arrow, right, in diamond shape. Okay, so this one you must label GM by pi, and then from B to E, you have R pi and V pi. Okay, and then what happened? Okay, what happened to your circuit? Okay, you just draw the all of the resistor that have inside the circuit. So here from V in, okay, from V in, the C1 is closed circuit. Okay, so your base is connected directly to V in because the C1 is closed circuit. Okay, C1 is closed, and then C2 also closed. Okay, VCC you must replace it with ground. Okay, when you do the DC analysis, AC analysis, sorry. So from C node, okay, from C node or C terminal over here, it is connected to V out. So from C, you connect it to V out. Okay, so you label V out, and then you have a RC connected to C. Okay, so from C also you have RC connected to C and ground. So you draw RC connected to ground. Okay, you have here RC. And then you must label the ZI, Z out. Okay, ZI, Z out, you must label. So here your Z out is pointing to the base. Okay, so it's pointing to the base. Okay, so here you have ZI pointing to the base, where over here you have R pi and RE. Okay, R pi and RE. And then for your Z out, okay, Z out over here, it is pointing to RE, right? Okay, I forget. At emitter you have RE, so emitter you connect with RE, and then your Z out is pointing to RE and RC. Okay, so here if you are confused how to draw the Z out, either it is pointing to RE only, you see the original circuit, RE and RC is in the same line or in the same column. So your Z out must be before or after the RC and RE. So your Z out is at the back of the circuit. So here is your Z out. So here, okay, here what happened is your Z out, okay, because in AC analysis, you know that you need to determine the Z and also the gain, okay, the AV gain. The gain, AV, AVOC, AV or AVS. So here, your Z out is easier because Z out is only referred to RC, okay. When you read the impedance at the output, it is pointing to RC because here is you open circuit your G amplifier. Okay, when you want to determine the Z, you open circuit your source. So here you only get the Z out equals to RC. Okay, this one is okay, easy. And then for ZI, okay, ZI is R pi and RE. Okay, you can see here your R pi and RE is a series or parallel.
Series.
Okay, your R pi and RE is series. Okay, in normal condition, you can just add. Okay, you can just add series resistors. Series resistors you add. So you add R pi plus RE. But for this case, okay, for this case, you cannot directly add. Why? Okay, why? Because the current over R pi is different compared to IE. Okay, when you want to add series resistor, the current must be same, right? But here your R pi, okay, your R pi has the current is IB, but your RE current is IE. Okay, and the value, okay, from the theory, IB is around micro ampere, but IE is around milliampere. Okay, it is very far away different. So what we can do, okay, what we can do is we use the Ohm's law. So from Ohm's law, what did Ohm's law says? Ohm's law said V equals to IR, yes. So V equals to IR, your V is VI, okay, your V is VI and the current that from the enter part is, here is IB, multiply with your resistor is R pi and RE. So here we can denote it with ZI. Okay, that's why here we use VI equals to IB ZI. So from this IB ZI here I already write. Okay, IB ZI we can separate it with another Ohm's law for voltage across R pi plus voltage across RE. Okay, that's why and then we get the VI because this is a parallel concept for voltage. Okay, and then from VR pi plus VRE we expand it. Okay, so VR pi we get IBR pi plus IE RE. Okay, before I go further, during AC analysis, okay, if you can see the label is using a smaller letter. Okay, your base using small letter, C small letter, E small letter, and the current also using small letter. IB, IE, IB. Here you have IC. So here you get the equation. You expand VR pi equals to IBR pi, right? And then plus IERE. Here you expand IE equals to IB plus IC. And then IC, okay, so IC here is equals to GM V pi. Okay, so we replace in the equation IC equals to GM V pi. Okay, so we get something like this. Or we can just replace it with beta IB. Okay, beta IB for IC. Okay, so if we replace it with beta IB, we get this equation. Okay, but if we replace it with GMV pi, we get a very long equation. So which one we want to use? Okay, which one we want to use is up to us. But because we want to find the ZI, okay, because we want to find the ZI must be VI over IB. So here if we reorganize the place, okay, VI over IB, okay, because we want to find the ZI, for this GMV pi, we get a very long equation over here. Or if we use 1 plus beta, our ZI will be equals to this one. Okay, so both are correct, but for ZI, if you want to find ZI with on the left equation GMV pi, okay, we don't know how much is GM yet, so we need to calculate our GM first. And then if we are using the right equation, we need to calculate the R pi value. Okay, so both are correct. Alright, but it depends on which one you want to use. Okay, so that the Zi will be equals to on the equation on the right or equation on the left. For our test or for our exam, what happened is usually we didn't ask student to prove the equation. Okay, we just want the student to determine how much is Zi. So if that case, okay, you can just remember the equation. But if you cannot remember the equation, you can do the derivation. Okay, no problem. Okay, you can just memorize or you do the proof equation. Okay, so here is your Zi value and also your Z out value. And then for another parameter that we can determine is the gain. Okay, the AV. So firstly, because the circuit didn't have any load, okay, any load resistor or VS, so this is a very simple circuit. We can find the AVOC. Okay, AVOC, OC is open circuit, no load, no VS. So if you want to find the gain, AV is V is the voltage, okay, so A is the gain, and then the gain is V out over VI. So here your V out, okay, your V out over here is equals to, just use Ohm's law, V out equals to VRC. Okay, so if you want to determine the VRC, okay, VRC, we can use the current over here, but here we have another current over here. VRC equals to the IC, the current across RC is different direction compared to the current over here, GM V pi. So we can put the notation negative GM V pi. Okay, this is the current actually. So this is the IC. And then we multiply with RC. This is the resistor. So your VRC is equals to negative GM V pi RC. And then VI, V at the input is parallel to V pi plus VRE. V pi plus VRE over here. So VRE is equals to IERE. You can use IERE. This one, IERE here. So IE, you can use the IE is about IC value. So you can use the IE equals to IC. So IC is equals to GM V pi. Okay, so you just replace V pi plus GM V pi RE. So GM V pi, we can simplify the equation, remove the V pi. Okay, so here you get AVOC equals to negative GMRC over 1 plus GMRE. Okay, so now if from the original circuit here, if we have another resistor, okay, why we don't use, if you still want to find IB value, which is, this is milli, this is micro. So here your IC may be around 2.6 milli. For example, okay, if you do a lot of exercise from the previous class, you can find that the IE and IC may be around just, the difference may be around 0.3 milli, around that value. So if your IC is something like this, IC is around 2.6, your IE may be around 2.9 milli. So it is not much different, because when we count the voltage, okay, the current milli value, we multiply it with the resistor. Resistor usually K ohm. So however the milliamp kilo will be the minute, right? So if you still want to use, IE value, you need to do a lot of works actually, because you need to find how much is your, all of the simplest value, you need to calculate it. But for example here, when you, in real world, you can just use device to measure the current, right? You can just use a multimeter or any meter to determine the value, because in reality, we didn't do the theoretical calculation. However, in your test, okay, usually the marks It's only 2 or 3. You don't have enough time to do a lot of calculation. For example, RC parallel to RE. RC parallel to RE. Okay, so RC is at C node. Okay, RE is at E node. Okay, so C and A, we cannot say RC and RE is parallel because the node or the connection is at the different place. And then there is another question. Why don't we need to include RE for Z out? Okay, this one. Okay, for Z out, when you want to measure the Z or the impedance here, you need to open all of the source, you need to open it. Means that when you do the Z out, determine your Z out, you need to open circuit this is called independent source, right? So you need to open circuit it. Okay, so here from terminal C to terminal E, the circuit is open circuit. That's why your Z out is only equals to RC. Alright, so next, when the circuit has another resistance at the V out. Okay, so this is the AC equivalent circuit at middle frequency analysis. Okay, so your ZI is still the same because your resistor is only R pi and RE. And then your Z out, because your Z out is pointing to before RL, so your Z out still pointing to only one resistor. So your Z still the same. But for your gain, AV gain will be different because V out over VI. So V out is equals to VRL equals to VRC, right? But the current here is only 1. So what you can do is you use the Ohm's law. Okay, the Ohm's law is IC, you multiply with the resistors. So resistors here are parallel, RC parallel with RL. And then here your IC, this is your IC. In order to determine the voltage over here, so the current must be flowing to this direction. So your I must be pointing to the voltage. Therefore, your IC is minus IC because different direction. So this is your V out. Okay, in the previous example, your V out is equals to negative IC multiply with RC. But now your V out is equals to negative IC multiply with RC parallel with RL. So we just expand this equation. IC is minus GM V pi. Okay, so you can just eliminate the V pi and then you get this equation for your gain. And then, okay, so now if we have a common collector circuit, so now the circuit also didn't have any bypass resistor over RE, okay, no bypass capacitor over RE. So here when you do the AC equivalent circuit at middle frequency, okay, so what happened here, you can see here your collector, okay, your collector is connected to VCC, and now during AC your VCC is 0. So you connect your C collector to connect it to the ground. Then your C connected to ground, base you connect to RB to the ground. So base, RB to the ground, and then emitter to the RE. Emitter to RE to the ground. And then your output, okay, so here your output is at emitter. Okay, output is pointing to emitter. So you can draw something like this. Okay, so it is pointing to the V out. And then you must label all the R pi and also GM V pi inside the BJT and your ZI, Z out. Okay, so your ZI is pointing to If you see here, Zi is pointing to the base node and also pointing to RB. So your Zi must be before RB, so it is in front. And then your Z out is pointing to RE, so your Z out is over here. Before this, your Z out is over VC, but now your Z out is pointing to emitter terminal. So now what happened is your Zi stay the same. Okay, so your Zi here is RB parallel with this resistor. So this R pi and RE, we have determined it must be, the series value is R pi plus 1 plus beta RE. Okay, so you can just use the equation instead of do the derivation. Okay, no problem. Then your Zi is RB, you parallel it with these two resistors. This is series, but because the current are different, so you must use R pi plus 1 plus beta RE. So for your output, your Z out, okay, so your Z out is RE. You know your Z out must be RE, but RE is connected in parallel with R pi and RB. So how much is this two value? Okay, actually for this two value also need to do derivation. For the derivation, I will include in the video, so we save time for this tutorial class. Right, so the values would be 1 R pi plus RB divided with 1 plus beta. So this one is a long, the derivation is longer compared to this series resistors. So here your Zi and Zi out is totally different equation. Okay, and then you need to determine your gain, your Vi and your V out. So here your Vi, okay, so here you can see I equals to VRB. Okay, Vi equals to VRB equals to, this one is V pi plus VRE. Okay, I have right over here, V pi plus VRE. And then VRE equals to GM V pi RE. So here we just use IE about IC value. Okay, so we have GM V pi RE. And then for V out, okay, for V out is pointing to emitter terminal. So we know that V out is equals to IE/RE. So IE we can use IE about IC value. So IC is GM V pi. Okay, so now how do you know that your GM V pi is positive or negative? Because here for this one, okay, why you take GM V pi positive? But in the previous example, you take GM V pi negative. Anyone can help?
Uh, GMV pi is positive because the current is pointing to VO.
Okay, yeah, you're correct. So it depends on which polarity for your voltage. So here, because the V out is same way with GMV pi, so you use positive GMV pi. Okay, so actually what is VS in the circuit? Okay, VS, usually we have another supply in front. So, but I just want to eliminate it first because we do the simplest first. Okay, when we master the simple circuit, we can proceed with a circuit with VS. Alright, so this is from, I think this is from BJT part 2. Okay, so BJT part 2, we have here. Okay, so here it says you have AC input. AC input is usually, maybe it be something AC input like this, or the circuit is connected to another resistors and also voltage source. So this is VS and this is RS. But when we do the, this one depend on the circuit, because if the provided circuit is without any RS or VS, okay, and then during mid frequency, we didn't need to draw the RSVS. Okay, so we take a simple first. So firstly, from DC analysis, for the circuit we get IC equals to 2.35 milliamp. Okay, so now we want to do the AC analysis. Please draw the ZI and Z out. This is output. So please draw ZI and Z out over here in the original circuit. Then here, GMV pi, you have at the emitter part, you don't have any capacitor here. So you have RE. Okay, so in your circuit, you have RE as well. Okay, and also here you have, at the output, you have RC. RC pointing to the C collector terminal and is connected to the ground. Okay, VCC go ground. So RC and then VCC over here. Here your Z out is pointing to RC and also RE. So your Z out must be at the back. Okay, so that's why your Z out is over here. And then you have AC output or V out. So V out is at the back as well. Okay, so this one you can use the previous ZI, Z out and also the AV to find the value. Okay, so try to calculate the ZI, Z out, also the AVOC for the circuit. Okay, maybe in 10 minutes. Okay, how much your ZI, Z out?
Z out equal to 2.2 kilo ohm. ZI tak kira lagi.
The IC equals to 2.3, so you can find GM equals to IC over VT. IC is 2.35 milli over 226 milli, so you get the GM. R pi equals to beta over GM. Beta is 50 divided with your GM, so you get the R pi value. Okay, do some more. ZI, Z out, and also AVOC. Okay, in a minute, 5 minutes. Okay, so how much is your AVOC? AVOC, anyone? V out equals to negative GM V pi RC over VI is V pi plus GM V pi RE. Okay, so equals to
Negative 2.176. Good.
Okay, negative 2 point. Negative 2.
Salah kira lah tu. Dia
21.7 ah. Negative 2175. Negative 19 milli.
negative 2.2.
2.2 right?
Uh,
RC.
Yes, I same with your answer, doctor. Negative 2.176.
Okay. So now this is a common base. This is a common base. Okay, common base. Okay, so your AC equivalent circuit Z out equals to RC. ZI equals to RE parallel with R pi. Okay, here because your R pi is here because the current is not the same as well. Okay, so what we can do is here this is the I have right over here. So you need to find what is the equivalent resistance over R pi. Okay, so here we can I indicate it with ZE. So ZE equals to V pi over RE, IE. So you get R pi over 1 plus beta. So for VI, okay, V in or VI equals to VZI equals to V in equals to VRE equals to V pi, right? Because this is a parallel. So VI equals to V pi and your V out, okay, V out because the current is pointing to the output. So the value must be positive. So GM V pi positive multiply with RC. Okay. AVOC, V out over V in, you get GMRC. Okay, this one is already simplified. Okay, so that's it for common base. However, common base usually we didn't use it because it cannot give higher gain. Okay, compared to common emitter and common collector. Okay, so this is an exercise. Okay, we do this first. Okay, this one. We need to add slide. We do the last exercise first because this is same with exercise 2. Okay, same with exercise 2. So how much is your IC for this one? Shall I continue from the previous exercise or we go one by one? I think
One by one.
there are some of you who haven't submit the exercise yet, but that's okay. Try to do on your own or maybe you can ask your friend and then try to submit it. Okay, so firstly, when we have the what is this? It's a pet. Okay, what we need to do is do the DC analysis first. So when DC analysis first. Here, what is the question asked to find? Okay, the question just want to ask ZI, Z out again. Okay, so here, because if we want to find the ZI, Z out, and again, we need to find the IC. Only IC during this analysis is the same with IC during AC analysis. So firstly, we need to determine our IC. So what we can do is, we do the Thevenin theorem. Okay, firstly, DC analysis to find the IC. So how to do DC analysis? Firstly is what we need to do is, during this analysis, we know our capacitors are
Shorted.
open circuit.
Open.
It cannot conduct current. Okay. So what's left on the circuit is, this one is open, and also open here. And then we simplified our circuit. So simplified here, we have R1 and R2, so we can use Thevenin theorem. Okay, so what happened to the circuit? I just draw. So we have VTH, RTH. Here we have IB, oops, VCC. This is RC, IC, this is RE. Okay, so firstly, determine your VTH and RTH. So VTH, how much? You know, right, how to find the VTH and RTH? VTH equals to R2 multiply with VCC divide with R2 plus R1. Your VTH. Then for RTH equals to R1 parallel with. Okay, so how much is your RTH? R1 parallel R2. This one you need to press your own calculator. VTH 3.52 volt. RTH equals to parallel 12 k ohm. Okay, so now you have your VTH and RTH. Now you can determine your current. So we can use the KVL1 or KVL2. Okay, so KVL1 or KVL2. Here the easiest is KVL1. VBE is CVE. So KVL1, I write it over here. KVL1 equals to VTH IVRTH plus VBE plus IERE. So here RTH plus VBE. IERE equals to IB beta plus 1 RE. Okay, so here you can find your IB equals to, how much is your IB? Masukkan nilai, put the values. VTH minus VBE divide with RTH plus beta plus 1. Ini tak boleh tulis. Beta plus 1 RE. So you get IB equals to, nampak IB tekan calculator, I get 30.3 micro M. IC equals to beta IB. Here beta is 8. So 80, 80 multiply with 30.3 micro, you get
2.43 milli.
2.43
43 milli.
milli. Okay, so here you have your IC, and then to determine your AC analysis, you need to measure your GM equals to IC over VT, 2.42 milli divided with 26 milli. And then you need to determine your R pi equals to, berapa equation dia? Beta over GM.
Yes.
Okay, so now you get your GM and R pi value. Okay. So now we want to draw the AC equivalent circuit. AC equivalent circuit here is. Okay, so firstly, if you want to draw AC equivalent circuit, the capacitor is, during mid frequency, the capacitor is fully charged, so it can conduct current. This one is short circuit. C1, C2, CE is short circuit, right? So, and it, tak mute. Okay. And then you draw the C, base, emitter. Okay, so here you have 3. For me, I like to draw, this is at input. Okay, input on the left. On the right is output. Down is ground. Okay, so input is connected to, so here is your VI is connected to base. So first node is base. And then output is connected to C. So I like to draw on the right the output. So C, here C. And then ground, emitter is connected to ground. Okay. And then draw the internal component of the BJT. So from B to E you have R pi.
Apa?
So you label R pi and V pi plus minus. And then C to E you have current. And then also need to label GMV pi. Alright. And then at the input, at the B here, base is to the input. So you have here R1 and R2. Okay, so you have, so R1 and R2 connected to ground. Right? And then from this node also you have RS and VS. So you just draw RS and VS. Okay. So here the input VI is pointing to the base. So base is over here and ZI is before R1 and R2. Okay. So ZI is over here and then VI is over here. Okay. And then at the output or at the collector you have RC connected to VCC. So VCC is ground. So connected to RC to VCC ground. And then from C connected to RL. RL to ground. And then put label V out at RL. And also Z out. Okay, Z out here is before RL. And pointing to RC and RE. So here is your Z out. Okay, so this is your circuit at AC equivalent circuit during middle frequency. Okay, so here you need to determine your, just now you already calculate your GM and R pi. And then you need to determine your ZI as well as your Z out. Okay. Oh, R naught. Okay. For this case, for our case, okay, R naught will always be infinity. Okay. If you draw, also okay. If you didn't draw, also okay. Alright. So your ZI, here you can see your ZI is, okay, so this is your ZI. So ZI equals to R1 parallel R2 parallel R pi. while your Z out equals to only one resistor. So Z out equals to RC. Okay, GM R pi tadi berapa? How much is your GM R pi? How much ni? 2 point
0.0931. Eh, ah,
90 milliamps.
0.0993 Siemens. Beta R pi
859.5.
tak apa lah. I just now
860.
read it. Okay, so your GM is, okay, so you just determine this. This RC equals to 1.2K. Okay, ZI ni berapa? And then you can find your gain. Okay, so firstly is you determine your AVOC. Equals to AVOC without RL. The voltage here is only this one. Okay? Okay? The output here is take this. So it is minus GM V pi multiply with RC divide with input is, okay, input is V pi, okay? All of these are parallel. So VI is V pi. Then you get the value. And then for AV, okay, so during AV you need to consider the RCRL, so I use different color. Okay, so AV is this one. So AV equals to negative GM V pi RC parallel with RL divide with V pi. Okay, so dapat AV. And then another one you have, okay, so this one. So how much is your AVOC?
111.6.
Apa 11?
111.6.
AV?
99.64.
Okay, so if you want to use equation, okay, instead of determine the using Ohm's law, you can use the equation is equals to AVOC multiply with RL over Z out plus RL. Okay, so this one you get
99.1.
okay, so you can choose to use Ohm's law or you can choose to use the equation. So it's up to you. And then we need to find the AVS. Okay, so AVS is equals to, you can use Ohm's law or you can use directly use the equation. AVS, AI, then you have AIS, and then also you can have power gain, AP, So P equals to AV multiplied with AI. Obviously. Okay, so for gain, okay, for the gain, if you get the gain negative, it means the signal is inverted, right? For example, you have VS, your VS is like this, and then at the output, your output is like this. Of course, this one is, if this is 1, here is 9. Okay. Okay, that's it for middle frequency analysis. Okay, dah siap ke everyone? Complete? Satu-satu. Okay. So AV here, AV is this one. AV is the voltage output divided with voltage input. So because AV, we will consider the resistor load. Okay, here in the yellow arrow, RC and RL are parallel. So we need to determine how much is the resistor over here to multiply with the total current. Alright, that's why you get AV, you get negative GMV pi multiplied with RC parallel with RL. And then for VI, here at the left side, or the input side here, VI is equals to VR1 equals to VR2 equals to V pi. Okay, so this is all the parallel resistors. That's why here for AV, your VI is equals to V pi. Okay, so here you can cancel your V pi. Can you see the slide over here?
Yes.
Yes or no? Yes. Okay, so this is from your e-learning. Okay, so from this part 3 notes. Okay, so part 3 notes. Remember for your AC analysis, okay, so for AC analysis, you will have mid. So you will have the range, and also at middle range of what we did just now is we want to determine the gain. Okay, over here you get the negligible effects from capacitors. That's why your capacitors during capacitor is fully charged or it is closed circuit. That's why you draw it as the circuit is short circuit, right? Okay, over there you get the gain. However, actually during frequency response or during the what happened before the middle frequency, actually there is also something happen over there. Okay, so before middle frequency we call it as low frequency, and after middle frequency we call it the during high frequencies. So for this one you need to draw a separate AC equivalent circuit. Okay, so you can have 3 AC equivalent circuit using hybrid pi model. First is during middle range or mid range, and then you can have during low frequency and also during high frequencies. So during low frequency, what you need to draw is the AC equivalent circuit with the coupling and bypass capacitors. And then during high frequencies, you need to draw the capacitance in active device, meaning that the capacitance inside the BJT. Okay. So first, low frequency. Low frequency, you need to draw the capacitors that you saw in the circuit. Okay. So you need to draw CS, CC, and also CE. So these three resistors you need to draw for your AC equivalent circuit. Right? So here. So on the left side is during low frequency, you need to draw the C, and then at high frequency, you need to draw the capacitance inside the BJT. Okay, so inside the BJT means you need to draw the, this is the effect for the depletion region. Okay, if you remember the between NPN, okay, so between N and P, there is a depletion region. So there is capacitance or impedance. So we need to draw the equivalent circuit for it. So here you can label it as CBC, CBE, and also here is CCE. Okay, so this another capacitance is in the wiring itself. So you need to draw the wiring capacitance at the input and also at the output. So for next class, we will learn about how to draw the AC equivalent circuit during low frequency and also during high frequency. Okay, so we will continue with the today example of the circuit. Okay, we continue on the next class. Okay, now it's already 1 p.m. Okay, so anything to ask before we dismiss?
No, doctor.
Right. So for the formula level on, actually the formula is inside your notes. This one, right? Won't ask the. So you can find the formula inside your notes actually. Right, so that's it. Thank you, class. Happy holiday. Next week is holiday, right? Next week is Raya. So
Okay,
next week.
doctor. Selamat Hari Raya.
Thank you, Doctor.
Thank you, Doctor.
Selamat Hari
Thank you,
Raya.
Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.